In this video, we are going to look at two definitions of the Dirac delta. This is our overview slide, which we'll spend less than 5 minutes on before going through each topic in more detail. This is actually, I think, a pretty short video, or I think it will be. We'll start off with a review, and that the Dirac delta function, when Dirac had developed this, it was a function that would be zero everywhere except at a single point, where the Dirac delta would be discontinuous and behave like an infinitely high, infinitely narrow spike of unit area. So this was the picture here. It's zero, the Dirac delta is zero, except at this one point, which we initially started at t equals 0, but then later generalized to t naught. So at t naught, we have this spike that's infinitely high, infinitely narrow, and area is equal to 1. So with this kind of curious definition, we want to see how we can kind of get a better understanding of this definition. So the first thing we'll do is we'll look at the Dirac delta as a limit of a sequence of functions. That is, our Dirac delta is the limit as n approaches infinity of a sequence of n functions, delta n of t. And we define that first with, so there are many functions that we can use to approach the Dirac delta in this way, and the simplest is the square function, which will define the delta of n of t is equal to n for t between minus 1/2 n and plus 1/2 n and 0 otherwise. And we get this here, and you can see at t equals 1, then when n is equal to 1, then our height is equal to 1, and we're going from minus 1/2 to 1/2. So this certainly, the area under here will give us 1. And then when we let n equals 2, you can see then our height is 2, but now our interval is going to go from minus 1/4 to 1/4. Again, our area is 1. Then when n is equal to 3, so we get this narrower spike but taller spike. So we keep going till n is equal to, well, infinity ideally, and we'll have an infinitely narrow and very tall spike, and the area underneath will be equal to 1. So that's our first definition. The second one will be defined by an integral operation. And in mathematics, this is how the Dirac delta is defined, and it's defined by how it behaves inside an integral. So we say this when we integrate between something to the left of t and something to the right of t, dt, of our Dirac delta centered at t naught times a function, it'll pick out this f of t naught if our interval that we integrate over includes our t naught and 0 otherwise. So any function which behaves like this Dirac delta is by definition a Dirac delta function, and this operation is sometimes called a sifting integral because it selects the single f of t naught value out of f of t. And this definition is consistent with this previous definition here. So that concludes our overview. So we'll go back and we'll start with reviewing the Dirac delta function, go through some more things, more detail, more examples. We start with this definition, just a review of the Dirac delta function. It's 0 everywhere except at a single point, which we'll designate as t naught. And it's discontinuous and behaves like infinitely high, which is why we designate this arrow with an infinity, infinitely narrow spike of unit area. And here is sort of the integral definition of our Dirac delta function. So inside an integral, when you multiply by a function and then integrate in this interval, if the interval contains t naught, then this definition will give you f of t naught. And if it doesn't contain t naught, then it'll be 0 otherwise. And if you think about it, it sort of makes sense because here, if you include t naught, then the Dirac delta is going to equal to the area is going to equal to 1, so you're going to get 1 times f of t when you evaluate it at t naught will give you f of t naught. And if you're not at t naught, it's going to give you 0. So this is the only place, right, that you're going to contribute to any area. And then if your interval does not contain t naught, so if it's like something over here, or if your interval is something over to the right, then your Dirac delta is going to be 0, in which case the whole integral is going to be 0. So that's kind of a review of what the Dirac delta function looks like. But now we're going to go through a definition, the sequence of function definitions, to kind of get some insight into how we can say we have this infinitely narrow, infinitely high spike where the area beneath the curve is equal to 1. So here we're going to start with our first definition of the Dirac delta as the limit of a sequence of functions. So we're going to have several functions, and we are going to call them our delta of n of t. And we're going to take the limit as n goes to infinity, and we'll see what the limit is. So there are many function sequences that approach the Dirac delta in this way, and the simplest is a square function defined this way. So dn of t is equal to n, with t going between negative 1/2 n and positive 1/2 n, and 0 otherwise. So remember, this is a sequence of functions. So let's look at the first in the sequence. That's delta 1 of t. And delta 1 of t is going to equal to 1. So this is our height of 1 when t is between negative 1/2 n, in this case n is equal to 1, so negative 1/2 to positive 1/2. So this here is our graph. It's equal to 1 between negative 1/2 and 1/2. You can see the area is equal to, well, the base is 1 and the height is 1. So the area is equal to 1. So that's our delta 1. Okay, again, it's a sequence of functions. So our delta 2, our second function, is going to be equal to 2 when t is between minus 1/2 times 2. Actually, this should be 1 over 2n. So minus 1/4 and positive 1/4. And 0 otherwise. So again, our delta 2, our second function, is equal to, has a height of 2 between minus 1/4 and 1/4, and it's 0 otherwise. And so here you can see my base here, also just looking at the area, my base is 1/2 times 2, so this total area is equal to 1. My next function, d3, which I'm going to write in blue over here, it has a height of 3 when t is between negative 1/6 and positive 1/6. So between negative 1/6 and positive 1/6, we have a height of 3, and it's 0 otherwise. And now you can see then here, the base of this rectangle is 1/3 times the height 3. You still get this area here, this shaded blue, is equal to 1. So what you see is as we go dn, when n is equal to 4, 5, 6, as we go higher values of n, we get bases that are narrower and narrower, but are higher and higher, have a, basically higher, but they all have area equal to 1. So in the limit, what we get is something that's going to be infinitely narrow, infinitely high, with area equal to 1. And that's kind of the intuitive sort of feel for this kind of odd or funny kind of definition. I had mentioned there are many function sequences that approach the Dirac delta, and we did the square function, but there are other common sequences that approach the Dirac delta. There's this resonance function, there's this Gaussian, and there's this sine squared function as n approaches, and as n gets really large, then all of this will get closer to 0 and we'll have a narrower spike that gets taller and taller. The sine function sequence approaches the Dirac function, but in a way that's different than what we've seen with this square function. And it's also discussed more in your book, but this is all I'm going to say about it, that you can also use it to approach the Dirac delta function. So this is going to be a short video. Anyway, the second topic then is the Dirac delta defined by an integral operation, and this is how it's defined in mathematics. And so the Dirac delta is defined by how it behaves in an integral. So when you take a Dirac delta function, you multiply it times some other function and then take the integral. Then if you're centered at t0 here, our Dirac delta is centered at t0, if your interval that you take the integral over contains t0, then your Dirac delta in this integral with this function is going to be equal to f of t0, and it's going to be 0 otherwise. So any function with this type of behavior is a Dirac delta function. And this operation is sometimes called a sifting integral because it selects the single value, f of t naught, out of your general function f of t. And this definition is consistent with the previous definition. And if you think about it, what it is, it's the same thing, because if you're at t naught, your Dirac delta is going to equal to 1. So then you're integrating and you have 1 times f of t, you plug in and f of t between on the interval negative t to the left and t to the right of t naught is 0 everywhere. So nothing's going to contribute until you hit t naught, and then you're going to get f of t. And then once you move away from f of t, your Dirac delta becomes 0 again, so no more contribution. So what you finally get is just f of t naught. Whereas if your interval does not contain t naught, then your Dirac delta is going to be 0, which makes the whole integral equal to 0. So I kind of moved all this information here about the integral operation and this sifting idea so that we can do some examples. These are the same examples I did in my previous video, so if you followed them and understood them then, you can just finish here. Otherwise, if you didn't follow, I'll do the examples again. This first example is the integral from 0 to 3 dt. Our function f of t over here is 2t squared plus 5, and then our Dirac delta now is centered at t naught equals 2. I can rewrite this so that my integral now, what's inside here, this 2t squared plus 5, the Dirac t minus 2, well, this is going to be my 2t squared plus 5 times, this will be equal to 1 when my interval includes my t naught. And here my interval is 0 to 3, so this is included, the 2 is included in my interval. If it had not been included, then my Dirac delta would be equal to 0, so this function times my Dirac delta would be equal to 0. So now when you do this integral and you're summing up all the areas under the curve, like we're interpreting the integral as areas under the curve, what you need to remember is when you're less than 2, everything to the left of your t naught, your Dirac delta is going to be 0. It's only when you hit t equals 2 that you get Dirac delta equals 1, in which case then you're going to evaluate your function at t equals 2. And then the moment you get larger than 2, between 2 and 3, your Dirac delta goes back to 0. So the only thing that's going to contribute to your area under the curve is t equals 2. So plugging that into f of t, you get 2 times t squared, which is 2 squared plus 5, which is equal to 13. For our next problem, it's nearly the same. The only thing that we changed, we had the same f of t, the same Dirac delta, it's our limits of integration. They're going to go from 0 to 1. Now when we look at this over here, our 2 is not included in our interval, so we're down here at the otherwise. So our Dirac delta is going to be equal to 0, so our function times our Dirac delta is equal to 0, so our integral is going to be equal to 0. So this example, to contrast with the previous example, shows that it's important to consider whether or not your Dirac delta, your t naught, is included in your interval. The last example is the integral from negative pi to pi dx sine of x, our Dirac delta x minus pi over 2. So our t naught, our Dirac delta, is centered at pi over 2. It is in the interval, so therefore this integral becomes sine of pi over 2, which is equal to 1. So to review what we've looked at in this video, we looked at 2 definitions of the Dirac delta. First, we reviewed the definition of the Dirac delta, which is 0 everywhere, except at a single point, t naught, where it's discontinuous and behaves like an infinitely high, infinitely narrow spike of unit area. And this was our definition here in terms of our integral. If we are centered at t naught, then our function f of t, our integral, will be equal to the function f of t naught if t naught is in our interval and 0 otherwise. So the 2 definitions we looked at, this first one was the Dirac delta as a limit of a sequence of functions. And this definition is kind of what helps me understand this kind of funny definition here, infinite infinitely high, infinitely narrow, the area is equal to 1 definition. And what we looked at is we looked at a sequence of square functions, and we defined that as our delta of n is equal to n for t between minus 1 over 2n and 1 over 2n, and 0 otherwise. And we looked at then d1, so when n is equal to 1, our height of our function is 1 for t between minus 1/2 and 1/2. And you can see you have this wide base, 1 unit high. The base is 1 unit across, so the area is 1. For d2, our second, this is a series of functions, our second function is at height 2 for t between negative 1/4 and 1/4. And again, you can see the area in the rectangle is equal to 1. And then for d3, our height is equal to 3 for t between negative 1/6 and 1/6. And you see the area of this rectangle is equal to 1. So you can see we can get narrower and narrower until we're infinitely narrow, and taller till we're infinitely high, and have an area equal to 1. This next definition is exactly this here that we had left off in our last video. So we define the Dirac delta by an integral operation. So as long any function, this delta t minus t naught, is considered a Dirac delta if, when you integrate the Dirac delta times a function between something to the left, something to the right, is equal to f of t naught when t naught is in the limits of integration, and 0 otherwise. And in this way, we call the Dirac delta a sifting operation because it essentially sifts out f of t naught out of your function f of t. And we did a few examples of this. So that's it for this video. Thank you for watching.